All right, welcome back. Got a couple things to talk about with AP exam changes before we actually jump in, but I'll go through the objectives and stuff first. So we'll be looking at an angular momentum FRQ problem, where we'll be comparing linear acceleration and angular momentum for an object that's sliding, sliding and rolling, or rolling but not sliding. So as we talked about in Calculus BC, there's been some changes for the AP exam this year. We're looking at 45-minute free response questions that are offered at home. There'll be 2 times where they're offered for each class, one earlier and one later, and you can pick which one you want to take. Every AP subject has some of their content that has been cut as well. So for physics, that means all of our unit on oscillations and all of our unit on gravity has been cut. Everything else is still on the test. Because it's only 45 minutes for the pre-response question, it is possible that the entire test will just be 3 FRQs. But those FRQs won't be on oscillations or on gravitation. Any questions on any of the changes? Okay. So unfortunately, what I was planning on doing today was oscillations. So I do have a free response question that I pulled from the same year that's not on oscillations that we'll be looking at today. However, I usually try to look through and solve these in advance. I haven't finished all of this one yet. For Calculus BC, since we didn't quite talk about all the topics that were affected, I've left you on this slide all of the topics that have been cut in yellow from all of Calculus BC. So that'll give you an idea of maybe what you don't need to focus so hard on before the test. Again, we only have 45 minutes to test, which means I'm expecting there to be 3 free response questions. And then that's it for Calculus BC. But later on, if you want to take a look at the slide, that'll help you inform how you want to study in the future. Any questions on anything happening at the AP exam? Okay, we've got a meeting with Mr. Jamal, the AP coordinator, and some of the other teachers at 2:15 today. So if we learn anything new, I'll let you know. On April 3rd, we should have those dates for you. Okay, so question for today. We have a ring of mass m, radius r, and rotational inertia mr squared. We're initially sliding on a frictionless surface at constant velocity to the right. So that means there's no friction from here. Oh, not writing. There is no friction from here to here. There is friction afterwards. So for all of L, we are sliding and rotating. And then after L, we have friction, but we are only rotating. Okay, so the first thing they want us to do is to start from Newton's second law in translational or rotational form and derive a differential equation that could be used to solve for the magnitude of the following as we are sliding and rotating. So this is in the green section. The first part, linear velocity as a function of time, and the second part, angular velocity as a function of time. Okay, so they gave us our start point. We're going to start with Newton's second law. So that's the sum of all of our forces has to equal mass times acceleration. Okay, right now, what's all the forces that are acting on this hoop? Okay, what about horizontally though? Should be something horizontally. Friction. So in the red section, there's no friction, but in the green and blue section, there is friction. So right now, when we're sliding and rotating, we do have friction. Okay, so that means our friction is going to be opposing our motion. So I could say negative F equals ma. Then what's our formula for a frictional force? Mu mg. Okay, I'm going to redo that last time. Mu mg equals ma. Okay, and I need a differential equation for velocity. So how could I rewrite this so that I have velocity in this equation? Perfect, that's a differential. Okay, so negative mu mg equals dv over dt. Okay, so what's our final answer? Minus mu g is dv over dt. Okay, so that's our first part. I wrote kind of big. I think I'm just going to add a couple slides once we get to it. I also want an expression for the angular velocity. So we'll start with what they gave us. Our torque is I alpha, and they gave us our I was mr squared. What's another equation for torque? F cross R, okay? So I could say torque is our frictional force times our distance that we traveled. So that's mu mg times R. I'm not using L because we want this to be a function of time. So we don't know that we've traveled all of L yet. Okay, then I can set these equal to each other and start solving. So torque is torque, mu mgr equals mr squared alpha. Okay, what are we solving for? Perfect. Okay, so let's do that. I'm also going to cancel out as much as I can in this step. So this is mu g over r is equal to the derivative of omega in terms of time. Okay. So that was A1 and 2, so we're on B now. I want to derive an expression for the following as the ring is sliding and rotating. First is linear velocity as a function of time. Okay, I'm going to go back. So we have dv over dt is negative mu g. How could we get an expression for the velocity at any time? We integrate it. Perfect. So this is the integral from what to what? Close. Okay, so my initial velocity to my final velocity. Because we already had speed once we started, right? Okay, for the other side though, I'm separating my variables first. So this is dv. On the other side would be negative times the integral of mu g dv, right? From what to what? Oh, sorry, dt, not dv. dt. From 0 to t. Awesome. Okay. So if I integrate, what's going to happen? Perfect. So I would subtract 0 on that side for my difference. Okay. And then we need to solve for v. So v is equal to v naught minus mu gt. And we've got our function for linear velocity at any time. Okay, then we also need an equation for our angular velocity at any time. So we had this one. Mu g over r equals dw over dt. So I'm going to start there. So I need some more slides. Yes. Yep, they still haven't announced the date yet. So as soon as the Chinese government says we're okay, so really the Shanghai Ministry of Education, then the school will give you 3 weeks notice. That way everyone has a chance to get back and go through the supervised quarantine if they need to. There's 2 weeks of a supervised quarantine if you're from an at-risk country. 2 weeks of self-quarantine if you're from anywhere else. Okay, we are on B2. We said dw over dt from part A was equal to mg over r. I need an equation for w, so what do I have to do? Integrate again. Okay, so this is separate my variables. This will be the integral of dw equals the integral of mg over r dt. What are my bounds? Okay, so I didn't point this out in the picture, but t equals 0 is right at the point where we start rotating. Okay, so the initial omega is 0. Okay, cool. So 0 to what? And perfect. What happens when I integrate the left side? Just omega. How about the right side? Perfect. Okay. GT over R. All right, that's good. That's it for B1, B2. We're on to C. I want to derive an expression for the time it takes the ring to travel distance L. The time it takes the ring to travel the distance L. What do I have to do? Okay, I've got an omega. How can I use it though? There we go. Okay, so V is equal to R omega. And we had a velocity formula from part B1. So I'm going to sub that in. V naught minus mu gt. V naught minus mu gt is equal to R times our omega formula, mgt over R. Okay, and now we've got an equation with t's that we can solve for. What do I have to do? Okay. Right. Okay. How do I solve for time? Is there anything else I can factor out? What else? There we go. GT and mu plus mass. Okay. Okay. And we've got an equation for t. Wait, hold on. That is mu. I can't read my own handwriting. This was our acceleration for friction. So this is mu. But I apparently can't read my own handwriting and skipped that for step 2. Okay, so that means this is mu. This is mu. And you're mu too. Okay, so what's our t? Okay, that looks good. Okay, that was C. Okay, then we're looking for D. Derive an expression for the magnitude of the velocity immediately after it traveled the distance L. Okay, so we had from the last one, our time was V naught over 2 mu g. Is there any equation that we could use to find the magnitude of the velocity after L? Are there any kinematics equations that could apply? Okay, so that is V is equal to what? Mm-hmm. I'm going to do my general kinematics form first. So the velocity is the initial velocity plus what? Nope. AT. AT is our velocity, right? So that's how much our velocity has changed. And then this is our initial velocity. So v is VO plus delta v, where delta v is our acceleration times time. Does that make sense? Okay. Then we can sub in. So v is v naught plus our acceleration. What's our acceleration? Okay, we said dv over dt is negative mu g. So our acceleration is negative mu g. Okay, times our time. Okay, so my mu g's can cancel. And it leaves me with v naught minus 1/2 v naught. So v is equal to what? V naught over 2. Okay, and the last one. Derive an expression for the distance L. Okay, that can work. So our kinematics equation would be dx is VOT plus 1/2 AT squared. So we're looking horizontally, not vertically. Okay, so our distance L is our velocity VO times our time, which we solved as what was our time? VO, not mu. VO over 2 mu g. Okay, plus 1/2 minus mu g times t squared. VO over 2 mu g squared. Okay. Then we need to solve for L. Okay, if I multiply this out, what happens? Okay. Eight mu g, because we've got that 2 from the 1/2. Okay, if I get a common denominator, what's going to happen? Okay, so that's 3 v naught squared over 8 mu g. Awesome. Any questions on anything we did? All right. Sorry, I know that was a little bit fast. I've got a couple people from the next class that are messaging me on WeChat right now. So I will see you tomorrow for Calculus BC. If you've got questions, please let me know on WeChat. And thank you very much for coming. Goodbye.